All right, now looking at example 9. Example 9 gives us a vertical oscillation problem. They tell us that the mass of an object connected to a spring is 0.20 kilograms. We assume the mass of the spring is massless, so we don't take that too much into account. They tell us the constant of the spring, and they tell us that the spring at the beginning is neither stretched nor compressed, and it is released from rest, meaning our V initial is 0, and it's neither compressed or stretched, so our initial position is 0. It says, in the absence of air resistance, how far does the ball fall before being brought to a momentary stop by the spring? How far it falls can be pretty much considered our max y, or our max amplitude, or our amplitude, really. And because it's going to fall, and then slowly starts to slow down, its final velocity is 0. And since we have no air resistance, we also know that the initial mechanical energy has to equal the final mechanical energy. Now, this whole is kind of crazy because, how can both our initial velocity and our final velocity both be 0? Isn't that going to cause a problem? Well, when we set up the math will hopefully fix itself and make it make sense. Since mechanical energy initial equals mechanical energy final, we have all our kinetic energies added together plus all our mechanical energies initial plus all our kinetic energy final plus all our potential energy final. And we can clean a few things up. Again, just like before, there's no rotating objects, so we don't have to worry about angular kinetic energy. Then both the initial and final kinetic energy are going to be 0 because it's being dropped from rest, and it's going to keep falling until it becomes at rest. And the potential energy of the spring initial is 0 because it is pretty much not stretched or compressed. It's at rest, which makes things much, much easier. Our potential energy due to gravity is mass times gravity times height initial. Our potential energy due to gravity final is mass times gravity times height final. Our potential energy of the spring is 1/2 k final position of the spring squared. If we assume that our initial height is at the unstretched equilibrium point that we started off with, and we call that 0, that would mean that our height final is negative xf. Now, it's negative xf because it's got a negative displacement, right? If the height at which it is unstretched is 0, then when it is stretched, it's going to have negative xf. And making our initial height 0 kind of cleans that up. So our equation becomes mg negative xf plus 1/2 k xf. We know our mass, we know our gravity, we know our k. We can solve for xf. Now, we have mg xf is equal to 1/2 k xf squared. We don't have to use the quadratic formula because if we just divide both sides by xf, we get a much cleaner formula that says mg is equal to 1/2 k xf. And we know our mass is 0.2, our gravity we're assuming is on Earth, and it's very close, so we call it 9.81. And we have 1/2 our spring constant, which is k, and xf, which is what we're trying to solve for. So when we solve it, we find out that this stretch point at which the velocity goes back to 0 because all the potential energy due to gravity went into the spring is equal to 0.14 meters. That's pretty much it.